Okay, let us work in this problem. Before we start, once more, let me just show you again very quick the procedure. Step 0, read the problem, do some type of figure sketch summarizing input, output. Basically, output is what you need to find. Then step 1, you need to do a figure that you will use in order to write down the main solving equation or equations. If you are able to solve at this step, you can just go to step 4. If you need additional information, you go to step 3. Okay? All right. So this is the problem. Let me read it. Ethane contained in a piston-cylinder arrangement undergoes a constant pressure process from an initial temperature of 50. So let's see. Piston-cylinder arrangement. So this is our piston-cylinder arrangement. It contains ethane, undergoes a constant pressure from an initial temperature of 50 degrees Celsius to a final of 100 degrees Celsius. Determine the amount of heat per unit mass, Q. Okay, so let us say this is step 0. Okay, step 1, many times is going to be kind of redundant, but it's a good habit to get, okay? So now you need to start thinking about, okay, now I'm really solving the problem. So first, what type of system are we dealing with? We'll be dealing with the system over here, which is a closed system because we know the mass is constant. Okay? Within the piston, if the pressure is constant, that means that this piston head is free to move up and down. And we know that the initial temperature is 50 degrees Celsius. We apply heat, and we end up to a final temperature of 100 degrees Celsius. And what we need to find is Q. Okay. So step 2, applying the first principle of thermodynamics. There's different sign convention, but in this case we use the Q minus W equal to change in internal energy. That's neglecting kinetic and potential energy. And using this definition, we know that the work done by the pressure is equal to positive PdV. Okay? All right, so over here there's 2 ways to solve the problem, and we're going to solve it both ways. So the first one, let's say here, okay, so I'm here, so we can write down Q will be equal to delta U plus work. Okay, so by definition we know this will be equal to M CV delta T plus P dV. Okay, and I was just reading the problem statement. Actually what we need to find is Q over M. All right, so basically we use the definitions for specific volume. All right, we can rewrite this equation here as Q equal to M CV delta T plus P dV. So V will be times M. Okay, so that the amount of heat per unit mass will be equal to CV delta T plus P dV. Okay, so this will be the main equation, and now if we put the data, we have Q over M will be equal to CV T2 minus T1 plus P V2 minus V1. Okay, so over here we don't know V2 or V1, so we need some additional equation. So we go to step 3, and we know that for the ideal gas, which is the ethane. Okay, so you see that's something I forgot to put here. Information is that ethane is an ideal gas. We know that we have, so for specific mass, the ideal gas relation become PV equal to RT. I think I demonstrated that on a previous video. Okay, and so from that equation, basically we have that V is equal to RT over P. Okay, so let me go to the next page. So now substituting the first equation in Latin into the star equation, we obtain Q over M equal CV T2 minus T1 plus P, and then V2 will be what? R T2 over P, remember P is constant, minus R T1 over P. So over here you see right away that you can cancel the pressure, and we're gonna have that Q over M equal to CV T2 minus T1 plus R factor T2 minus T1, or if we simplify, Q over M equal C sub V plus R T2 minus T1. Okay, so now we are almost ready to solve. So we know we have ethane as a gas, as an ideal gas. We go to table A, not A2E, but table A2 to find the value for the CV. So from table A2, which on the Zengel textbook is on page 883, you see that for the ethane, didn't give you the R ethane, let's see, so here, So the R constant is 0.2765 kilojoules per kilogram Kelvin, and you see that the CV is equal to 1.4897. Okay, so now we can go to step 4. And basically step 4, we're gonna have Q over M equal to 1.4897 plus 0.2765. Okay, now if you want, you can move, you can transform the temperatures into Kelvin. Okay, but if you put the temperature into Kelvin or Celsius, you will agree that the difference will be the same. So you can keep it in Celsius in this case. So it will be 100 minus 50. So after plugging these values in your calculator, you will get a result in kilojoules per kilogram, a value of 88.3. Okay, it's really 88.265. Okay, so the second procedure, so let's say it will be the N solution 2. I'm just going to do a little bit faster over here, but if you remember the definition for specific heats for a piston at constant pressure, and this is our system, the amount of heat going into the system we say will be equal to M C sub P delta T. Okay, so from that equation you will have what? Q over M equal to Cp delta T. And if we did things right, you will see that the Cp should actually be equal to the Cv plus R. Okay, so from table A2, we have that Cp is equal to 1.7662. Okay, which actually should be the summation of those two values. So let me just double check. 1.4897 plus 0.2765, 1.77662. So basically you see right away that if now substitute, we have Q over M will be equal to the 1.7662 times the 100 minus 50, which is identical to this. So we'll get the same result, 88.3 kilojoules per kilogram. Okay, if you decide to do it this way, you still need to go through the steps 0, 1, 2, 3, and 4. Okay, but here I think will be a little bit of repetitive. All right, thank you for your attention.